going to talk about miniaturization of spectrometers. The outline of the tutorial is as follows. I will make some introductory remarks, and then I give you a short historic overview. And because I'm already so old, it's much easier to give you a historic overview. I worked with very large instruments at the beginning of my career. The more I appreciate that I can hold them in a hand now. I give you, and I apologize in advance if it's a very simple introduction, because I did not know about the heterogeneity of the participants. It's spectroscopy light. It's not spectroscopy zero, it's spectroscopy light. On Raman, mid-infrared and near-infrared, I will talk about the building principles of these handheld instruments. And then, most importantly, I will talk about applications, qualitative and quantitative applications, how you can use them. Introductory remarks. Based on the interaction of radiation with matter, these three techniques I'm going to talk about, Raman, mid-infrared and near-infrared spectroscopy, can identify, discriminate, and quantify a broad range of materials. I think I'm a little bit an outlier in terms of this conference, because these techniques can really tell you, is it compound A, B, or C, and they can assign correctly the investigated material. And because, I mean, these techniques are relatively old, some of them, they date back many decades, but miniaturization has further launched these sensors, let me call them sensors, into a new era of analytical tools. Mass verification is certainly an extremely important process if you want to know exactly how much mass you have in a container during a linear motion or during free fall. And this is very important, for instance, but you have to know, you have to be sure of the chemical identity of the material. You have to be sure that what you dose is what you want to dose. Think of pharmaceutical industry. There you certainly have to know, if you fill a blister cavity, you have to know that this is a mixture of active ingredient and excipient. But this sensor does not tell you about. He tells you about the mass of the material and not the quality of the material. And that's why once again, I stress that the techniques we are talking about, they tell you something about the identity of the material. Short historic overview on the miniaturization in vibrational spectroscopy. This was in the mid-70s. This was an infrared spectrometer, Fourier transform infrared spectrometer, 2.5, it needed almost a separate laboratory, a small room. It weighed 250 kilos. 20 years later, it had shrunk already considerably. And another 10 years later, it was already portable with high modularity. This is an FT-NIR spectrometer. These is a Fourier transform infrared spectrometer, and you can exchange these modules in order to measure in transmission, in attenuated total reflection, and in external reflection technique. Same in, this was mid-infrared and near-infrared. Same in Raman spectroscopy. This is the Raman spectrometer. And these are handheld Raman spectrometers today. And this is an instrument which just came out a couple of months ago. So nowadays you can put a mini laboratory for vibrational spectroscopy on a small table. However, speaking about handheld spectrometers, this is the reference scale. weighs 60 grams, 2.5 wave numbers. Here it is connected with a USB cable to a laptop. Nowadays, it's used wireless with an Android system. This dates back to 2012. Now, a short introduction to the principles of quality. And again, I apologize if it's too simple for you. Just look on your phone and concentrate back later on. What is spectroscopy? Is the interaction of light with matter. Newton showed that light consists of different visible components, but there was Mr. Herschel who detected there is also something beyond the visible region. It's the infrared region. And he further elucidated the phenomenon of absorption. So what did he do? So generally, the phenomena we are talking about is transmission. You have a source of radiation, a sample, and a detector. You measure the transmitted radiation, thereby you measure the absorption. You can measure reflected radiation. These are infrared and near infrared. And if the sample scatters inelastically, it is a Raman effect. So what did Newton and Herschel do? Newton detected this region. This was easy. You can detect it at home. If you look behind your window, sometimes you have these stripes on the ground. But Herschel took a thermometer and he put it beyond the visible region where he didn't see anything. And then he gradually moved it into the visible region, and he realized that the temperature is increasing. So from this, he concluded that there is electromagnetic radiation beyond the visible region, which is visible, and which is actually near infrared, mid-infrared, and far infrared. And I realize some of you have just been in the terahertz talk. Terahertz is far infrared. And different wavelength regions have different energy. So the wavelengths we are talking here in this tutorial, they are embedded between the kitchen and the ductor. So we are here. That's what we measure. Herschel did another experiment. He took a sample, he measured the temperature before the sample, and he measured it after the sample. And the temperature decreased. So he assumed that the sample absorbs. So wherefore does the sample use this absorbed energy? It uses the absorbed infrared radiation to excite vibrations. And you can imagine, the more complex a molecule, the more vibrations are possible. A nonlinear molecule with n atoms has 3n-6 degrees of vibrational freedom. A simple example, water. 3 atoms, 3 times 3 is 9, minus 6 is 3, so we have 3 vibrations, okay? Symmetric stretch, antisymmetric stretch, and deformation. Here you deform an angle. And how does a spectrum look like? That's a spectrum. So, So we have the deformation here. The antisymmetric is the left wing, and the symmetric is the right wing. Just a word of caution. Think of polymers. Polymers are very long molecules with a huge number of atoms. Now, if a molecule has a molecular weight of 20,000, you may think that it must have a huge number of absorptions according to this 3n-6. It's much easier because these molecules, these polymers, are built up by a repetition of monomeric units. You focus only on the monomeric units. So the vibrations of the long chain are more or less redundant. So you can use it to investigate polymers very nicely, actually. the origin of the IR spectrum. So if you offer the sample a number of wavelengths or polychromatic radiation, it will absorb those wavelengths it needs in order to excite specific vibrations. And it will then absorb at these different wavelengths in different ways simply because there are different excitation conditions or different oscillators absorb differently. Now let us compare the basic principles of Raman mid-infrared. Now it gets a little bit more serious. Of Raman mid-infrared and near-infrared. It's anharmonic. Such an atomic oscillator oscillates anharmonically. If it would oscillate harmonic, this would be a parabolic shape. But because it's an anharmonic oscillator, you call this a Morse function. Potential energy versus distance of these atoms. The reason why you reach this plateau is simply because if you extend the bond too large, it breaks. The point is reached where it breaks, the bond breaks. So, first of all, we have an anharmonic oscillator, and now let us focus on the wavelengths or wave number regions. So, mid-infrared and Raman are identical and they are complementary. And near-infrared is of higher energy because it focuses on overtones. You need higher energy in order to jump from the ground energy state to the second, third, or fourth energy state. Let's start here because this is the easiest. In mid-infrared, we focus on fundamental vibrations, and fundamental vibrations are vibrations where you just go over one energy level from the ground state to the first excited state. These are the fundamental vibrations. This arrow is fat simply because it has a fundamental vibration has a much higher energy, a much higher intensity than a first overtone, a second overtone, or a third overtone. Because the probability to jump over 2, 3, or more energy levels goes down. It's the law of Boltzmann. So these two techniques are absorption techniques, and you illuminate the sample with a polychromatic source, which means a source which offers all wavelengths. In Raman spectroscopy, the principle is different. You illuminate with a laser, with a monochromatic laser, either in the visible or in the near-infrared, which means one wavelength only. You offer the sample one wavelength, you excite it to a very high energy level, it's a virtual level, and from there it can come back to the first excited state, and this energy difference corresponds to this energy difference. And this is normally what you measure for conservative Raman spectroscopy. It is a so-called Stokes line. If you start at the first excited level and go back to the ground state, the same energy difference, it's an anti-Stokes, but the probability to start at the first level is lower, so the intensity of anti-Stokes is lower than Stokes. So Raman spectroscopy, conservative Raman spectroscopy focuses on the Stokes lines. The problem of Raman spectroscopy is here. The intensity of the Raman line is only 10 to the minus 8th of the excitation line. That's why you have to use a laser in order to see a Raman spectrum. This is just one of the problems. There is another one. We are going to talk about this. So the information is contained in the absorbed radiation for mid-infrared and near-infrared, and it is contained in the scattered radiation for Raman. So this is a scattering technique, and these are absorption techniques. So this is just a repetition of what I have shown you. You can also go back to the ground state after excitation, but you do not want this Rayleigh line. You want to get rid of it. This is a Stokes line, anti-Stokes, and the intensity of the Raman line is only 10 to the minus 8 of the source and 10 to the minus 4 of the Rayleigh line. So you have to get rid of this Rayleigh line. You do it by filtering. What is the difference between a fundamental and an overtone? Just to give you a feeling, very easy. It's double the frequency or half the wavelength. And that's what so this would be mid-infrared, and this would be near-infrared first overtone. The excitation conditions, very important. Why do we see a signal in infrared and near-infrared on the one hand, and why do we see a signal in Raman spectroscopy? In infrared, we see a signal if there is a change in dipole moment during the vibration. Just imagine you have a carbon atom and you have an oxygen atom, and these two vibrate. The oxygen is negative, the carbon is positive. By vibration, you change the dipole moment. So the carbonyl functionality is a very important functionality for mid-infrared. And you see it very intensively in mid-infrared. In near-infrared, you have the same condition. However, there is an additional limitation. And this limitation is that the mass of the two oscillating atoms is very different. In Raman spectroscopy, you focus on you have to have a change in polarizability during the vibration. Polarizability basically characterizes how easy it is to deform an electron cloud. Just think of a carbon-carbon double bond. You have an electron cloud between these two carbons, and if you deform these two carbon atoms during vibration, you get a very intense signal in Raman spectroscopy. So change in polarizability you need for Raman, change in dipole moment you need for mid-infrared and near-infrared, and there additionally you have to have a large mass difference. So you basically focus only on a very limited number of functionalities in near-infrared. CH, OH, NH, 12, 1, 16, 1, 14, 1. So it's not very selective, this technique. That's what you think. Raman and infrared are complementary because Raman basically focuses on homonuclear functionalities or homonuclear vibrators, oscillators, whereas mid-infrared focuses on polar functionalities. Both have high structural selectivity compared to near-infrared, but you can enhance the selectivity by chemometrics, by statistical techniques. Quantitative analysis for mid and near infrared Beer's law. In Raman, a logarithmic relation between intensity and concentration. In Raman spectroscopy, you have a direct proportionality between the intensity and the concentration. And by intensity, I mean either the peak height of such a signal or the peak area of a signal in the Raman or infrared. This is a univariate approach. If you take one signal and you focus on the peak height or the peak area, you call it a univariate quantitative evaluation. If you use large spectral areas combined with statistical methods such as partial least squares, PLS, you can also use it for near infrared. Of course, you can also use it for Raman and mid-infrared, but here very often you get on this univariate evaluation. So this is certainly a negative effect here. Instrumentation, sampling, and process control. In mid-infrared, we are focusing primarily on Fourier transform infrared. you have a large variety of techniques in near-infrared grating, Fourier transform, acousto-optic tunable filters, diode array, or linear variable filter. And in Raman, you have either the NIR excitation or the visible excitation. And you use Fourier, in some cases, Fourier transform technique or charge-coupled devices. Sampling and process control, you don't need sampling for Raman and for near-infrared. So you don't have to prepare the sample for the measurement. You use it as it is, which is, of course, very important for process control. In mid-infrared, you have only one technique where you do not have to prepare the sample, and this is a so-called attenuated total reflection. I will show you later how it works. In Raman, you focus, because you focus your laser beam, you focus on a very small portion of the sample. So you have to make sure that this small spot of the sample is representative for a large sample, except you have a flow-through system. In the ATR technique, you focus on a very small thickness, only a few micrometers. So again, you have to be sure that this surface is characteristic for the whole sample underneath. And the advantage of near-infrared, the advantage of near-infrared is that you can focus on large thicknesses, up to centimeters, depending on the concentration or dilution of the sample. You can work with light fibers, which means you couple the instrument and separate it from the sample measurement point. For instance, you have an instrument in a control room, you have light fiber, and bring it to the reactor, the same here for these two techniques. In mid-infrared, it is limited. There are different probes available, at-line, in-line. Here, transmission, diffuser, reflection probes, and here you have ATR probes, attenuated total reflection probes, which focus on a small thickness only. So this is a big plus. The thickness here, the light fiber capability, and the variability of instrumentation. What information can you get from near-infrared and Raman spectra? You can get information on chemistry. Constitution, which means is it a certain compound, is it an additive, is it an impurity? Configuration, if you have a double bond, is it cis or trans? But you also get information on physics. Conformation, just think of a protein. Is it a helix or is it a beta-pleated sheet? State of order. Is it amorphous? Is it crystalline? Is it a blend of amorphous? Polymers are never purely amorphous or purely crystalline, most of them. In most polymers are semi-crystalline, which means partly crystalline, partly amorphous. And is it oriented? Just think of a fiber. All the polymer chains are oriented in the fiber direction. So you get a lot of information from these spectroscopic techniques. Just a few examples. Mid-infrared spectroscopy, different polymers give you absolutely different spectra, and these spectra are fingerprints, forensic fingerprints of this polymer. Now I show you the same with Raman, and I show you the same with near-infrared. However, now take, you want to make a photo? Yeah. I can send you the presentation. It's no problem. Taken from pharmaceutical. This is an active ingredient. You take it for a headache. I worked for Bayer for a long time. That's why I've shown it. This is an amorphous excipient. A material you mix, you blend with your active ingredient because you use only a very relatively small amount of active ingredient. Again, it's a fingerprint. Can you see specific differences between these two? If you look at the width of the signals here relative to these sharp signals, this is a crystalline material. This is an amorphous material. So you see chemical and you see also physical properties. There is one enemy. The colleague next door had talked about an enemy for terahertz: water and metal. For Raman spectroscopy, you have two enemies also. The one was that the intensity of the Raman signal is just 10 to the minus 8 of the laser. The second is fluorescence. If you excite with an NIR laser, in most cases you stay within this Morse function. And then you come back to, for instance, the first excited state. And this gives you this Raman signal. If you excite with visible radiation, you may get out of this Morse function into the next electronic state, and from there you can go back by fluorescence. And fluorescence inundates your Raman spectrum. And you don't see a Raman spectrum, you see mainly fluorescence. So a compromise, because the scattering efficiency also goes with the force power of the Raman excitation, you have two counter effects. The one is the increasing fluorescence if you go from NIR excitation to visible excitation, and the other is the decreasing scattering efficiency. So a good compromise is the 785 nanometer excitation line, which is just in between. And most Raman systems do have this laser in order to excite the Raman effect. This is a typical case. This is the Raman spectrum of SiO indigo measured with an argon laser. And this is the Raman spectrum of SiO indigo measured with a neodymium laser at 1064 nanometers. You have shifted to the near infrared. Visible excitation, of course, it's an extreme example. If fluorescence persists at 785 nanometer excitation, recently, Rigaku Raman Technologies has come out with this instrument I've shown you. It was shown the first time at the Pittsburgh conference in March this year, the so-called progeny. And again, this is an alginic acid sodium salt and pharmaceutical excipient, and this is a Raman spectrum measured at 785 nanometers, so it is not a good compromise for this material. Even at this excitation, fluorescence persists, but if you shift to the near infrared, you get a very good Raman spectrum. Building principles of handheld Raman mid-infrared and near-infrared spectrometers. I show you the building principles of these 6 instruments. Of course, there are several others on the market. So there was, for instance, A2 Technologies. They have now changed to Agilent. And Agilent has changed dramatically because handheld was an exaggeration because it weighed 4 kilos. You had to be Arnold Schwarzenegger in order to handle it a whole morning. So what they have done very cleverly, they have changed the center of gravity from here to the handle. And thereby it is much easier. It is also lighter a little bit. But it is now much easier to handle this instrument. So you can see not only instrumental details, sometimes also design details could be important in order to change the, the possibility to handle an instrument. This is an interesting alternative for a mid-infrared ATR spectroscopy. This is a zinc selenide crystal, and you simply put your material, in most cases a liquid, onto this area. It's mostly for oil and petrol, gasoline measurements. You put your material on here and you measure the mid-infrared spectrum. The enabling technology is a linear variable filter, and we will have a look at this in more detail. There are other handheld instruments available. And here you have also 785 nanometer as well as near-infrared excitation. So let's have a look. What's inside in this Raman spectrometer? You have the laser. You have a little light fiber, which brings it to the Raman probe. So this is the exit of the spectrometer, and here you focus your laser on the sample. And the sample can have any sort of morphology, any sort of shape. So basically this part here is this nose. And here you focus on the sample. The backscattered radiation is brought back with a light fiber to the spectrometer. Here you have a grating, and here you have a charge-coupled device chip, which is thermoelectrically cooled. So you do not need liquid nitrogen or something. For instance, for a handheld instrument, it's impossible. So everything is packed into this little instrument. Yeah. You will see it in the next. And this shows you a spectrum measured on a laboratory instrument, paracetamol, pharmaceutically active ingredient. And the same spectrum, it cuts off a little bit earlier. It does not show the CH stretching vibration region. Spectral resolution is here. 10 wave numbers. It has a 785 nanometers, focuses on a spot size of 200 micrometers with a focus of approximately 2 to 3 millimeters. It's also thermoelectrically cooled with a CCD detector with 2048 elements. And it can be operated between -30 and +60 degrees. And a colleague who worked for this company, it is now sold by Thermo Scientific, but originally it was designed by the company Ahura. And this colleague from Ahura told me they had sold 3,000 systems to the soldiers in Afghanistan in order to detect materials. This is the black one. The 2 wave number resolution refers to the black spectrum. No, the spectral resolution. Yeah. Yeah. Yeah, it's very similar. The problem is the 10 wave numbers, the signals are broader than the spectral resolution. So you at that point, you don't, if you would measure a gas, probably you would see the differences, yeah, but not for this material. And they can operate at different temperatures. You can drop it. It's shock-proof. They offer libraries now. They offer also qualitative and quantitative chemometric evaluation packages. This is an info. So it's all these three, and this is one of the problems. All these three instruments now belong or are commercialized by Thermo Scientific. And this means for quite a long time, this company had a monopoly. And you know what monopoly means. Monopoly means this. So shrinkage in size is not shrinkage in price, unfortunately. The instruments are still quite expensive. What I've shown you is the 3 instruments on the table with a laptop behind, where I said a micro vibrational spectroscopy laboratory you can put on a table. It will cost you something like $150,000. The 3 instruments, $50,000 roughly. So one of these instruments here will cost you $50,000. It's almost the same price like a benchtop instrument. That's a problem. Okay, what's in the mid-infrared system? You have an interferometer. You have a Michelson interferometer integrated, a source, a beam splitter, a moving mirror, a fixed mirror, and from both mirrors the radiation comes back and falls on this single bounce diamond ATR plate, gets in contact with your sample. The sample has to have contact with the diamond surface. That's important for the ATR technique. And from there, it goes to the detector, a deuterium triglycine, deuterated triglycine detector. Maybe I should go back here. This is important. It covers almost the whole mid-infrared region with a very good spectral resolution of 4 wave numbers. 4 wave number resolution is perfect for solids and liquids. You don't need more. Not for gas analysis, but for solids and liquids, perfect. Again, you can operate it at -20 to +40 degrees centigrade. Its temperature, shock, drop, proof, etc. It also has libraries. It also has chemometric packages. And this is the ATR technique now in a benchtop instrument. So how does it work? Your radiation falls on the diamond, and there you bring your sample in contact with the diamond. It slightly penetrates into the sample and then comes back into the diamond and in the focusing element in order to go to the detector. The sampling depth is only a few micrometers, and this is exactly the depth you need for mid-infrared, because in mid-infrared you can focus only on very thin samples. So you only bring your sample in contact. So for a liquid, you put a droplet of the liquid on here and you get a perfect spectrum. If you have a paste or a soft material, it's perfect. It gets more difficult for a hard material. And the penetration depth is given by this formula, and it is wavelength dependent. And that's a big difference to transmission spectroscopy, because if you compare transmission to ATR, in transmission, for the individual wavelengths or wave numbers, the thickness of the sample remains the same. But for ATR, it increases. So you cannot compare an ATR spectrum with a transmission spectrum. You have to correct it. There are correction procedures available. But you have to think of it. If you have an ATR spectrum and you subject it to the library of transmission spectra, you may fail, and vice versa. So I told you, if you have hard samples, you have a specific crusher available. So you put your material in here, and then you press this crusher against the diamond surface of your FTIR ATR spectrometer in order to press the sample against the diamond surface. The diamond surface is mechanically and chemically very stable. So you will not be able to scratch it. They have also libraries, and they have software packages available. Near infrared, so we had now Raman, we have IR, now we have near infrared. This is an exploded view. You see the largest weight comes from here. And this is optical heart of the instrument. It's a microelectrical mechanical system. So you measure either in a reflection or in transmission. Of course, the light source is always on the same. They just wanted to show that you can either measure in transmission or in a reflectance. Then it falls on this MEMS chip, first on a grating, set on the MEMS chip, and then eventually on the detector. How does this MEMS chip work? The MEMS chip works like a mini piano, relatively easy. You have dispersed already the radiation here on the MEMS chip. And these individual piano keys are operated by a voltage. Like the piano player pushes it down, you apply a voltage, it goes down, and then it allows a specific wavelength to be deflected. All the others remain in the same position. And in that way, you can move up, move down and up again one piano key after the others, and thereby select the wavelengths you would like to send to the detector. It's a little bit more complicated, but this is a basic principle. And you can easily discriminate whether it's polyester. So if you go to China and you buy a shirt, they normally tell you it's silk. And I tell you normally it's polyester. And you can prove this very easily. These two Raman Technologies, I show them because they have a specific grating. So you have your laser, a light fiber. You bring first, you go to the sample. From there, the Raman scattered radiation comes back and is brought to the grating before it falls on the in-gas detector, the thermoelectrically cooled in-gas detector. This instrument is a very new one, and you see again, the weight comes from the batteries mostly. This is the optical heart where you have the laser. Here you have your sample, and then it comes back, falls on this specific grating before it goes to the detector. Now, what is the difference between a conservative grating? This is a so-called Cherney-Turner. The radiation falls on the grating, is dispersed in the different colors. In the transmission grating, there is a slight rotation of some optical parts, and you transmit the grating, and the detector is behind. According to Rigaku Raman Technologies, the advantages are higher spectral efficiency, increased sensitivity, ruggedness, and lower cost. I cannot see that this is not as robust. I'm not absolutely sure, but I would be careful. But spectral efficiency, yes. The advantage of Raman spectroscopy is that you can put your focus, for instance, through a dark bottle into the liquid, so that you get only a spectrum of your liquid and not of the containing surface. With mid-infrared and near-infrared, now with mid-infrared you are completely lost because you would get only a spectrum of the dark glass, or you actually would get nothing in that case. Even for near-infrared, you would, if the radiation would go through the glass and would be reflected back, you would have double absorption of your glass. And if this is a brown glass, it will absorb also near-infrared. So you would have a superposition of glass plus sample. But here, you get the Raman effect only from the focus which is in the liquid. So the blue spectrum is the ideal case where the focus is in the liquid. The red is an empty bottle. The focus is in the bottle, but there is nothing in the bottle, and you don't see anything. And the green is the focus in the brown bottle, and then you get fluorescence. Finally, we spend most of the work with this instrument at the moment because it's so easy to handle. The enabling technology is a linear variable filter. And the company which commercializes this instrument, they are specialists, GDSU, they are specialists in depositing thin layers very correctly and very controlled on substrates. And this is actually the case here. So you have an assembly of different layers, and they have these layers have a wedge geometry. This is important, so that if polychromatic radiation falls on this wedge geometry, and this part, this optical part, fits on the fingertip of my small finger. This is the size, so that you can imagine the size. So different positions allow only different wavelengths to go through. And this is the dispersion activity or dispersion capability of this linear variable filter. These are the materials used for the deposition of these layers. They offer two systems. One for the 950 to 1650 nanometer region, which is close to the visible, or 10,500 to 6,000 wave numbers, or the extended version from 1100 to 2100 nanometers, or approximately 9,000 to 4,500 wave numbers. Uncooled in-gas detectors, 128 pixels. The resolution is not impressive, but I will show you examples that you can use it to discriminate and quantify materials. You can measure in reflection. So you put this, it's like the head of a stethoscope. You put it on the sample and measure it. Or you take the source out of the instrument, put it on a sort of specific, how would you call it, on a metal plate, where you have the possibility to put a liquid sample in between before it falls on the spectrometer. And you measure in transmission. To give you a feeling about the differences in spectroscopy in terms of spectral resolution between a benchtop instrument, which measures from 4,000, actually they measure from the Bruker instrument, and many other NIR spectrometers measure from 4,000 to 12,000 wave numbers. Here is a mid-infrared region, and here is a visible region. This is the extended version of this micronear. And if you now look, we are focusing on this region here, from here to here. All the features are here. But they are less, they have less fine structure. But the information is here. And if you use chemometrics, you can extract this information. Discussion of selected qualitative and quantitative application examples. First example, or one of the examples we used for Raman spectroscopy was that a colleague from another city was coming to us. He came from the aluminum industry. He represented the aluminum industry, and he said the aluminum industry uses diluted sulfuric acid a surface treatment agent. Now, concentrated sulfuric acid is toxic. And the environmental authorities are thinking of banning the use of diluted sulfuric acid for this application. However, Raman spectroscopy can clearly show that the ionic structure of concentrated and diluted sulfuric acid is completely different. And with a handheld spectrometer, and we compared it to a benchtop spectrometer, both instruments were used a laser in the near infrared for excitation, so it was an NIR excitation. And we also used a benchtop instrument in order to have the comparison between handheld and laboratory instrument. And we showed that this could actually be tested on site if necessary. So if an agent of such an environmental authority, he could come to the company and really test there the concentration of the sulfuric acid. These are three different. The laboratory instrument, 96 concentrated, 80%, 20%. And look at the Raman spectra, completely different. Same spectra with the handheld instrument. Everything is reproduced perfectly. Now let us look at the assignment. Concentrated sulfuric acid is almost non-dissociated. If you start diluting it, you create HSO4, primarily HSO4 minus ions. And if you go a step further, you further change the ionic concentration. If you look, for instance, here at SO4 2 minus, this vibration here, which is not here in the concentrated and in the 80%. Bitumen in road construction work. Now, if you ever had bitumen in your hand, it's a disgusting material. Sticky, oily, terrible. I would have never expected that it is possible to measure an infrared spectrum from this material. So for road construction work, the bitumen is blended with polymers, with additives, with polymers in order to change the rheological and adhesional properties. And it would be interesting, I don't know, it would be of interest to the road construction companies, but it would be interesting for the authorities to be able to control the composition of bitumen. And the question was, can FTIR, ATR be used for this purpose? And can we even use a handheld system for on-the-road analysis? Again, we have made parallel measurements with a laboratory instrument and a handheld instrument, but I show you only the results for the handheld instrument. This is a small silicon rubber plate, and the bitumen is here. You just put the diamond of this nose here in contact with the bitumen. The bitumen is relatively, gives a relatively good contact with the diamond. These were the measurement parameters, and these are the spectra. Perfect spectra, and you were not be able, actually we have cut out some regions because the diamond absorbs in a certain region and gives a very bad signal to noise ratio, but this is the same for the laboratory instrument, because there you also use a diamond as a reflection element. So the spectra of the laboratory instrument looked absolutely the same. And then we prepared calibration samples, and this is a very difficult task because you have to add different amounts of polymer to this bitumen, and you do it at 160 degrees centigrade and you stir it. It's not an easy task. You stir it several hours in order to get a homogeneous blend. And we developed calibrations with different amounts of this polypropylene maleic anhydride polymer additive in the bitumen. Of course, you see that there is some variation. We calibrated and we cross-validated this, and based on this calibration, we predicted samples which were not contained in this calibration. This is important. And this is a prediction relative to the calibration, to the reference value, because these were also prepared by admixing the polymer to the bitumen. And you see, with the exception of this sample, the results are agree very well and good enough for on-site, on-the-road measurements. And we went even a step further. You can also correlate the spectra with other physical bitumen properties like needle penetration. Needle penetration is a rheological measurement. You measure the force you need in order to push a needle a certain distance in the bitumen. And the reason why you can do this is because obviously the chemistry of this bitumen has an impact on the spectrum, on the mid-infrared spectrum of this sample. Determination of counterfeit and illegal generic pharmaceuticals. This was done with a small instrument here. This is a NIR instrument. This is a powder. So you measure diffuser reflections. The radiation comes from the sources in the instrument, falls on the powder, and is diffusely reflected back onto the detector, on the monochromator and on the linear variable filter and the detector. As an example, weight loss product, counterfeit and authentic, and you see immediately the differences. This is a counterfeit, and this is a original. And if you go to the second derivative, you can see it even better. Contamination of soil with hydrocarbons. Imagine you have a truck, you have an accident, and gasoline, diesel, oil is spilled. At present, for fast on-site identification and determination of the amount of contamination, you have to rely on laboratory methods. And the question is, because the remedy measurements to be taken are either biotechnical methods or excavation methods. If it's too serious, you would like to know, and you would like to know it quickly. How much do I have? What do I have? Is it diesel? Is it gasoline? Is it oil? And at the moment, it's difficult to find techniques which can do this on site. So we have used a handheld NIR instrument, not the very small one, the somewhat larger one, in order to quantify gasoline separately, gasoline, diesel, and oil in the range up from 1,000 ppm, 0.1% in soil. This was a measurement, petri dish with a contaminated soil. And these are calibration spectra we developed. So you see, these are you can see there is no absorption here. This is pure soil on the bottom. And this is a concentration of about 10%. And you see clearly the CH combination and overtone vibrations of the CH groups, in that case, of the oil. We did it separately for diesel and for gasoline. We developed a calibration based on the second derivatives, a PLS, partial least squares regression. This was a calibration. You see, we had very good values here. There was a little bit scatter here. I don't know whether it was a heterogeneity of the soil Also, we made replicate measurement in different positions in order to make sure to have representative, but we had a larger scatter here. And then we predicted samples which were, of course, not contained in the calibration. This is important. And now compare the prediction with the reference. So I think it's a suitable prediction accuracy down to a certain threshold value. But we also wanted to see, can we discriminate whether it is oil, gasoline, or diesel? So in order to do this, we took spectra of pure soil, of course replicate measurements, of soil contaminated with gasoline, with diesel, and with oil. And we developed a principal component analysis. This is water here, this region. We cut out the water because we wanted to be independent of the humidity of the soil. So we cut out this spectral region and used only this region and this region in order to be able to better separate. And this is a score plot of the principal component analysis. And you see, you can relatively nicely discriminate the clusters of the pure soil from the gasoline. This is a little bit more difficult because diesel and oil is very similar. But it is possible to discriminate it as long as your concentration has a certain value. So above about 1.5% contamination, you can discriminate diesel from oil. Another NIR project, geological test samples. The company which came to us is a global player in bauxite exploration. What they do is they go to different places, they take samples, and they would like to know very quickly, is it worth to carry on exploring this site because the aluminum content is high enough to guarantee us that we have success in mining. And it would be nice if we can do this on site. They can mill the rock samples very finely. Perfect, you get a very fine powder. I don't know what they use, but probably like a coffee mill, but a little bit stronger. So they send us 90 different samples with different aluminum content, and which we used for calibration, and then they tested us with 14 unknown samples. We used a laboratory instrument, again, now in comparison to this mini instrument, because this would be very convenient if the engineer could have it in his pocket and measure it directly on site. But of course, based on a previous calibration. So these are the spectra of two samples, where the blue spectrum represents a sample with no aluminum content, and this would be a good sample. It would be worth carrying on to mine. And we did the same. It is actually only a small region of the spectrum of the laboratory instrument. And this is only this region because the instrument does not extend over a larger region. But you see the features are completely reproduced, of course with lower resolution, but the information is here with a small handheld instrument. And this was a calibration we developed of samples between 0 and 60, not 60, 55 or 53% aluminum. And based on this, we could, I don't want to say perfectly, but good enough predict the aluminum content in order, with approximately 5% accuracy, we could predict the aluminum content of the test samples, where they did not give us the values, they sent us the values later on. So it is a potential tool for on-site geological exploration studies. And this is my favorite example. Authentication of seafood by near-infrared spectroscopy. The company who sells this mini instruments, they send us a publication of FDA, Food and Drug Administration, from 2010, where it was pointed out that there are lots of problems in seafood marketing due to mislabeling of products in the harvesting or processing chain, to species substitution at the restaurant level, etc. And the question was, is it possible to undertake something against this fraud and deception? And to develop a fast and reliable analytical procedure to take suitable countermeasures. We tried to use this mini instrument for authentication by principal component analysis in combination with so-called soft independent modeling of glass analogies. It's a chemometric procedure which requires a previously run PCA which is then fed into the SIMCA algorithm in order to discriminate gases. Two fish, a red mullet from France, $56 per kilo, and a mullet from Senegal. I forgot to put the fins up. You would not be able to discriminate these two fishes. And this black spot is not specific for the mullet, I should say. We have investigated. We made these photos at the beginning because we were very excited about this technique. This is a typical measurement of the fish. This is the instrument, and this is assembly. This is another fish. I should say I went to our fish shop, and I'm not an expert in fish investigations. I like to eat fish, but I'm not an expert. So I went to our fish shop and I said, can you tell me, do you have pairs of fish which look very similar with different price? He said, oh, I could tell you a lot. So I said, give me. So we bought fish. I had to eat. I was eating fish 3 weeks together with co-workers. So this was a measurement. Classification by SIMCA of this fish pair. So I show you the classification of these two fish. We made many different measurements of fish from different, of course from the same place, but different days, etc., in order to have representativity. So what you normally do is you run a principal component analysis for the spectra you measure of one class. So in that case, we had two principal component analysis of red mullet and a principal component analysis of mullet, of the cheaper one. And then these two PCAs were introduced into the SIMCA algorithm. And what this algorithm does is that if you have two classes, he puts the spectra of one class in this quadrant. He puts the spectra of the second class in this quadrant. And now you test with a spectrum of an unknown fish. Could be either the cheap or the expensive. And you want to know, is it the cheap? Is it correct? Or did the fish shop give me a higher quality fish for a lower price? No, certainly not. It will be the opposite, if at all. So if the test spectrum ends up here, you know it's a high quality fish. If the test spectra end up here, you know it's a cheap quality.
What do you mean by quality?
What's that?
What do you mean by quality?
By quality?
Quality. How do you make it?
That's a quality? No, I measure it only by price. And why do you think the one costs 50? We did not make a DNA analysis, just to make sure, yeah? But I can tell you one thing, the information is in the skin of the fish because we measured the skin. My wife filleted it, and we measured also the meat. The discrimination via the meat is much more difficult or almost impossible compared to the skin. So the information is obviously in the skin. If it's here, it's a shark or any other fish. It could be, I haven't shown it, it could be also here in this quadrant. Then it's difficult to discriminate. Then obviously it's a case which you cannot discriminate. In our case, it was very easy. So it does not belong to either class here, of course. So this was the starting position here, and the grays, but the blacks were the test. So it was an expensive fish, and he was correctly identified. And this was the other case where we tested a cheap fish, and he ended up in the correct class of the cheap fish. Conclusions? I hope I have shown you that it is possible to use these small instruments or handheld instruments for on the road, on-site analysis, and generally these handheld spectrometers provide an excellent, at least alternative to laboratory instruments for qualitative and quantitative chemical quality control, and these are some acknowledgements, and of course I thank you for your patience to stay here so long. Thank you.